Okay, so from our previous video, we saw that when you equate y prime with a times y plus f of t, you end up with this series of equations right here. And this is actually 4 equations compressed down to 2 because we have different coefficients on the constants and on the t's. So from the first equation, you will notice that if we equate the t variables, the first power ones, we're going to have a 5b1 plus a 3b2 plus 3 equaling out to 0 on the left-hand side. Then if we equate the constants, we're going to have a 5a1 plus a 3a2 plus nothing equals a b1. And now if we take the b2 equation and do the same thing, our t is going to give us a negative 6 b1 minus 4 b2, and that is going to be equal to 0. And then if we compare constants, we've got negative 6a1 minus 4a2 plus 4 equaling out to the constant b2 on the other side. So this is a 4x4. It's actually a 4x5 linear system because we actually have a right-hand side. So this is going to be in matrix form. Looking at the A1s, we've got 0 and 0. We've got 5 of the B1s, and we've got 3 of the B2s. And we have a negative 3 when we bring the constant over to the other side. All right, and then for the next one, we're going to have a 5 in the A1 location, a 3 in the A2 location, a negative 1 in the B1 location, 0 in the B2 location, and a 0 on the right-hand side after we move the B1 over. And then the next one, we're going to have zeros in the A1 and A2 location, a negative 6 in the B1, a negative 4 in the B2, and a 0 on the other side of the equal sign, and then a negative 6, a negative 4, and then 0 for B1, a negative 1 for the B2 when it comes over to the other side. And then we're going to have a negative 4 on the right-hand side. We can now take this 4x5 linear system and substitute into our row-reduced echelon form of our calculator. And when we do that, we end up with the A1 number working out to be negative 9 halves. The A2 number is going to be 11 halves. The B1 number, let's see if I can write that a little better. The B1 number, as we said, is equal to a negative 6. And the B2 number is equal to a positive 9. So our yp of t then is our constant matrix A1, A2, which is negative 9 halves and 11 halves, plus our matrix vector B, which is negative 6 and 9, times t. That's in vector form. And then as one single vector, that's negative 6t minus 9 halves and 9t plus 11 halves. And again, this could actually be taken back and substituted into our differential equation. Y prime is equal to ay plus our f, and it will make a true statement upon substitution in place of the y's.